Welcome back, everybody. In the last video, we looked at one way of making new functions from existing functions would be to add, subtract, multiply, or divide two functions that we already had, or to form the function composition with two functions that we already have. So what we're going to do in this video is look at another way of making new functions from old, and that is by forming transformations of functions that we already have. So let's get started. So there's several different transformations that we can apply. We're going to start with one of the simpler ones, and that would be a vertical transformation or vertical shift of a graph. So taking a look, suppose that we have a graph of a function f shown here in blue. If we wanted to consider the graph of f of x plus c, then that would be the graph of f shifted up by c units. And then if we went to think about the graph of f of x minus c, of course, where c is a constant, that would be a vertical shift of the graph, but downward by c units. Here, all of this is assuming that our c is positive, okay? So basically, if you have a graph of a function f, if you add a constant to it, that shifts the graph up. If you subtract a constant from it, that shifts the graph down. To illustrate that, I wanted to think about the graph of y equals x squared, one of our basic toolkit functions, the basic parabola with its vertex sitting at the origin. I'm figuring out some function values in a table here. I chose x values between -2 and 2, just integer values, because they're nice and easy to calculate. And I have that here. X squared is 4, 1, 0, 1, and 4 for x values -2, -1, 0, 1, and 2. If I wanted to calculate now x squared plus 3, this would be, well, I don't need to go back to x, right, and start with that. Can't I just take x squared and add 3 to it in each case? So x squared is 4, so x squared plus 3 will be 7. If x squared is 1, then x squared plus 3 will be 4. If x squared is 0, then 0 plus 3 will be 3. And then continuing the pattern, we should end up with 7, 4, 3, 4, 7. All right, I've just taken the values for x squared and added 3 to it. For x squared minus 4, we'll take the column for x squared and we'll simply subtract 4 from it. So x squared minus 4, in the first case, will give us a 0. In the second row, 1 minus 4 will be -3. Then 0 minus 4 will be -4. And again, we can continue that pattern down for the rest of the column. So taking a look at it, we want to think about how we would draw this, right? So for x squared plus 3, we would be keeping the same x values, but our y values for points would be 3 larger. For x squared minus 4, our y values would be 4 less. So let's actually fill in the details for that graph. All right, so down below here, I've produced the graph of y equals x squared, or at least a piece of it. I've only graphed it from -2, 4 to 2, 4. Of course, the graph realistically would keep going upward, but I'm not going to draw that part just to keep our graph a little bit simpler looking. All right, so I want to add to the graph x squared plus 3. So let's do that. I'm going to do that in blue, so let me color code that. So when x is -2, we should have 7. When x is -1, we should have 4. When x is 0, we should have 3. And then, as you know, the graph has some y-axis reflection symmetry, so that you can exploit here. When x is 1, y is 4. And then when x is 2, y is 7. So if you just form the mirror image across the y-axis, then you've got the right idea there. So it should look like the blue graph is essentially the kind of light purple graph, but scooted up by a couple of units. For x squared minus 4, let's draw in those points, we'll have -2, 0. And then -1, -3, 0, -4, 1, -3, and then 2, 0. we? All right, so the green one here should look like the purple one, but pushed down by a couple of units. So the overall here is that you have, if you have a graph of a function f, if you add a value to it, then a positive value, then that scoots the graph up by a couple of units. If you subtract a value, then that will push the graph down by a few units. For horizontal shifts, we want to take a look at horizontal shifts next. For that, I think making a table of values is not as easy to see. So instead, I want to think about it in terms of where do important points get moved. So we're going to do it in that way. And to do that again, we will use the x squared graph. Because this one, it ends up a little bit counterintuitive. For the up and down graph, it was pretty straightforward. After all, plus in the y direction, plus is up and minus is down. For this one, if we're going to graph f of x minus c, here c is again positive. For x minus c, it's a right shift by c units. For x plus c, it is a left shift by c units. And in the x direction, we're used to thinking of to the right for positive and to the left for negative. Here, inside the parentheses, you're seeing x minus c for a right shift and x plus c for a left shift. All right, to kind of see or make some sense of that, we've already drawn the graph of y equals x squared. So let me make a rough sketch of that here. The graph of y equals x squared is a parabola and has its minimum value at the origin. That's the lowest point on the graph. And if you think about it with real numbers, which is all we're doing here, the smallest answer you can get when you square a number is going to be 0. So let's think about what the graph of x minus 2 squared would be. Let me call that g of x. If you have x minus 2 squared, let's think about that for a second. What would g of 0 be? G of 0 would be 4, right? Not 0. So g of 1 will be 1 minus 2 is negative 1 squared is 1. Could you get something smaller than 4 or 1 out of this g? And the answer is yes. What would it take for you to get 0 out? If you were to get 0 out, that would be because you had to put in 2 for x, right? So can you get anything smaller than 0 when you are squaring? Answer is no. So the smallest that you can get is when you have a 2. G of 2 will equal 0. That suggests that the minimum point for g of x is going to be at 2, 0. It is a right shift of the graph. Okay, let's try that again, different function. Let's think about a function h of x, and we'll make that x plus 3 squared. Okay, so h of 0 is 9. H of 2, that's getting even worse, right? 2 plus 3 is 5 squared is 25. Okay, here we're squaring. We have x plus 3 squared. What can I substitute in here for 0 in order to make, in here for x, in order to make it so that 0 comes out? So the smallest answer you can get if you square something is going to be 0, and that would have to happen if you're putting 0 in and squaring it. So what does x have to be in this case? X would have to be negative 3, right? H of negative 3 is going to be negative 3 plus 3, that's 0. 0 squared is 0. So that suggests that our graph here is left shifted by 3 units because its minimum point is at negative 3, 0. So far what we've got is if we're going to add a constant, that pushes a graph up. If we subtract a constant, that pushes a graph down. And that's vertical. For horizontal shifts, it's a little bit less intuitive. Here, keeping in mind that c is positive. For x minus c, it's a right shift. For x plus c, it's going to be a left shift. One other thing to keep in mind is that when we're graphing a function, we're graphing a function y equals f of x. Our x is the horizontal axis. Our y, or our f of x, is the vertical axis. In the first case, we were adding this constant c after the f of x. It was f of x plus c or f of x minus c. So that means that the adjustment was done to a y value, which is why the graph moved in the y direction. The graph moved either up or down because the plus c, or the adjustment, so plus or minus c, was done after the f. In the more recent case, we're adding or subtracting c to what? We're adding or subtracting the c to an x value. If we're adding or subtracting our c to an x value, that means that our movement is going to be in the x direction. That is left to right. So remember, if you're doing the adjustment on x, the movement will be in the x direction. If you're doing the adjustment to an f of x, the movement will be in the y direction. For the y direction moves, it's pretty intuitive, plus for up, minus for down. And then for the horizontal direction shifts, it is kind of the opposite of what you might think. And how to keep straight which way it's going to go, you can think of transforming some function that is familiar to you, like the x squared graph as we have here. So these first transformations have been about moving the graph up and down and left and right. This next part has to do with reflecting graphs. For reflection, the graph is either reflected across the x-axis or across the y-axis. And so basically here, let's take this first one first. It says if you want to graph y equals minus f of x, then you're reflecting the graph in the x-axis. To see why that's so, let's think about that for a minute. Here, you know what the graph of y equals f of x looks like. This would be taking all the y values and putting a minus sign in front. So any y values that are positive would turn negative, and any negative ones would turn positive. So for example, if you have the graph of the square root function, which looks like that. We saw that when we did a little linear approximation a couple of sections ago. All those y values are positive. But if we keep the same x and turn all the y's negative, then we're going to have the graph of y equals minus the square root of x. That reflects the graph across the x-axis, okay? If instead, here we're making the adjustment in x values, if you're making the adjustment on the x values, we're now reflecting in the x direction. If we're reflecting in the x direction, we're reflecting across the y-axis. So let's see an example of that. We had the graph of the square root. Why not stick with that? The graph of the square root of x looks like this. If we wanted to take the graph of square root of minus x, that would look like this, reflected across the y-axis. All right, so this has been a look at a couple of transformations. We have a few more to do. I wanted to show you a couple of graphs on the computer before we proceed. I'm going to be using this website, desmos.com/calculator, to get this done. So let's go ahead and take a look. All right, so we're taking a look at desmos.com. I've put on here the graph of y equals x squared. And so let me add to that the graph of another function. Let's make y equals x squared minus 3 or minus 2. So the purple graph, you can see now, is shifted downward relative to the red graph. Let me add to this the graph of y equals x squared plus 5.1, let's say. Okay. There's the black parabola. You can see that the black one is shifted up relative to the red one. One of the nice features of Desmos is that you can use a slider here. So I'm going to do that now so that we can illustrate that better. Let's make y equals x squared, and then we're going to use another letter. I'm going to call that A for this. Let's see if we can use C like the textbook. That's good. All right, so when you type a C, you can see it gives a little exclamation point, and it'll ask you if you want to add a slider or not. If you click on the C, it will go ahead and add the slider. So you can see, oh, that's unfortunate. They're both red. Let me see if I can fix that. Oh, well, it didn't keep it. I wanted to change that because it made both the functions red, which is kind of a bad choice. Let's see if we can get something better. Okay, there we go. We got one blue now. So let me make that a little better looking. So now that we have a slider in here, if you take the little blue dot here, you can drag it to the left or right, and you'll see that that moves the graph up or down, right? If you take and make the C higher, the graph moves up. If you make the C smaller, it moves it downward. If the C is negative, now the blue one is below the red one. Of course, when it's 0, it exactly will match. So here we've taken our function, we've scooted it the graph up or down. We could try this with another function. Let me use the square root graph. Okay. All right, and we'll see that this behaves in the exact same way. Again, a positive C will move the graph up, a negative C will move the graph down. Okay, so that's how that looks for C. It was vertical translations. Let's take a look at some horizontal translations. So for a horizontal translation, instead of the adjustment being in the X direction, instead of the adjustment being in the Y direction, it's in the X direction. So we're adjusting our X values. So here we'll have X minus C. For a positive, our original function here is in red, our adjusted one is in blue. If we have X minus C where C is positive, the graph is shifted to the right by C units. And then if we have X plus C, then our graph is shifted to the left by C units. Okay, let's try that with a different function. Let's use, we haven't used an absolute value function yet. We'll cover the absolute value function in more depth in the next section, but we've seen it already in our toolkit of functions. Okay, so here's our original function shown in red. Our shifted function is shown in right. For positive C values, if you take X minus C, the graph shifts to the right. And then X plus C, the graph is shifted to the left. There's our original function. For X plus C, that shifts the graph to the left. Okay, so far we've seen a couple of horizontal and vertical shifts. Let's see if we can pull off a reflection. For the reflection across the x-axis, let's just make this y equals minus the absolute value of x. So here you can see that the graph is reflected across the x-axis. This one's going to look kind of dumb if I try to reflect it across the y-axis, right? Think about it for a minute. Let's take the graph of 1 over x, our reciprocal graph. Okay, so this is the graph of 1 over x. It's undefined at 0, right? Let's take and make the graph of y equals minus 1 over x. All right, so that's reflected across the y-axis. You could also look at it as being reflected across the x-axis as well. So let's use a different function for this. Let's go back to y equals square root x. That's fine. All right, so there's our graph of square root x and square root of minus x. So I wanted to show you some pictures on the computer illustrating these transformations. I'd recommend to you, if you're interested, to try this on the computer and practice just typing in different formulas and see what kind of graphs you get. And then that will give you a better feel for those transformations. All right, so in the last couple of transformations, the transformations didn't really change the shape of the graph. They more or less changed the position of the graph in the XY plane. In the next transformation, it actually changes the shape of the graph. Here we're looking at vertical stretching and shrinking of graphs. So here, again, for this part, C will be either a positive number between 0 and 1 or a number that is bigger than 1. If we have C bigger than 1, we're looking at how multiplying by a number C affects the shape of the graph. If the graph is multiplied by a number bigger than 1, it stretches the graph vertically. What you're seeing here in the picture, the original function is shown in blue, and then the red function would be the shifted one. It's multiplied by our C. If instead you multiply by a number less than 1, then that's going to compress the graph vertically in the direction of the x-axis. So let's see why that might be so by taking a look at the graph of the y=x² function. So I've repeated our table for the x² function that we drew earlier. I have again x values from -2 to 2, and then x² is 4, 1, 0, 1, and 4. If you were to make the graph of 5x², you'll notice that we're just taking the values for x² and multiplying them by 5 for the same x values. So I'm not going to draw this actually, you can just think about it. For the same x values, we'd have y values that are much bigger. But you'll notice that we haven't added anything to the 0. The 0 is still a fixed point, so the graph is just stretched in the y direction. If we were to make the graph of 1/8 x², again, keeping the same x values, we now have very small y values of 1/8, 1/2, 1/8, 0, 1/8, and then 1/2. So that is going to be a vertical stretch of our function. Again, if we're multiplying by a number bigger than 1, it gets taller. If we're multiplying by a number less than 1, it gets smaller. So again, I want to show you a couple of graphs on the computer. All right, so this part we've seen before. We have the graph of x² and also the graph of x² plus 2. So the red graph will be our original graph for this, and then the black one is our shifted graph. Here, you'll notice as before, we've moved the graph up by 2 units, so the vertex is at 0, 2 for this one. If instead of adding a constant, if we multiply, make it 2x², you'll see that, sorry, unfortunately, that one is red again. Let's take it out. There we go, blue's better. All right, so here you can see that instead of shifting the graph up, you'll see that the vertex is in the same place, but the graph should look like it's been stretched vertically relative to our red one. Again, if we make a bigger value, it should look even steeper. In fact, let's go ahead and make a slider for this. So here they coincide because we're multiplying by 1. The bigger that we make our A, our multiplier out front, the steeper the graph will look. If we make it less than 1, sorry, got away from me, it's going to end up wider. Let's try that with a different function like the square root graph. Okay, so then here we have our regular graph shown in red. Here our A, I guess it was a C in the book, so let's use a C for this. All right, so our multiplier C, if you multiply by a number bigger than 1, it's now stretching the graph vertically. It's not moving the graph up altogether, but it's just stretching it vertically. If you multiply by a number less than 1, it's going to squish the graph vertically. And then we can throw on a -1 as well. So this one, -0.7, that would reflect the graph across the x-axis and also compress it. So this should look like a compression of our original graph and also reflect it across the x-axis. Okay, so multiplying by a number bigger than 1 stretches a graph vertically. Multiplying by a number less than 1 will compress the graph vertically. So what we're going to look at next is another way of kind of characterizing functions called looking at even and odd functions.